What if empty space isn't actually empty? In 2022, a telescope in Australia caught something that's been messing with physicists ever since. A radio burst from 8 billion light-years away, lasted less than a millisecond, but carried more energy than our sun produces in 30 years. That's not the wild part, though. The wild part is what that signal picked up on its way here. Matter we've never been able to see, scattered across billions of light-years of space, we thought was basically nothing.
Empty space is actually full of these quark and gluon field fluctuations. And on average, it is possible to annihilate a quark from empty space because it's not empty.
In this video, let's get into exactly what FRB 20220610A actually revealed. Fast radio bursts weren't new in 2022. Scientists had been detecting them for years. But when FRB 20220610A hit the ESCAP telescope in June of that year, the researchers looking at the data basically stopped and said, that can't be right. So let's talk about what ESCAP actually is, because it matters here.
The country's National Science Agency said on Tuesday that what's called the Australian Square Kilometre Array Pathfinder was able to map out 3 million galaxies in just under 300 hours.
The Australian Square Kilometre Array Pathfinder is a network of 36 dish antennas spread across the Western Australian outback, and they all work together as one big detector. The whole system is designed to scan huge swaths of sky simultaneously, so it's not pointed at one specific spot waiting for something to happen. It's more like a wide-open eye watching a massive chunk of the sky at once. That's actually how it caught this burst, not because anyone knew where to look, but because ESCAP was just sweeping through and the signal hit it. Like catching a camera flash in the background of a photo you weren't even trying to take.
The telescope has a wide field of view thanks to receivers designed by the Commonwealth Scientific and Industrial Research Organisation, which allow it to take panoramic pictures of the sky in greater detail than before.
Now, the burst itself lasted less than a millisecond. To put that in physical terms, a human blink takes somewhere around 150 to 400 milliseconds. A single neuron firing takes about 1 millisecond. FRB 20220610A was shorter than that. So the obvious question is how you even detect something that brief. And the answer is basically that ESCAP is recording continuously, and the signal was strong enough to show up clearly in that data despite being almost instantaneous. And that's the part that didn't make sense. A signal traveling for 8 billion light-years should be incredibly faint by the time it reaches us. Space isn't a perfect conductor. Energy spreads out over distance, and 8 billion light-years is a genuinely enormous distance. But this signal wasn't faint. The energy reading was way outside what researchers expected. Here's a comparison that actually helps land how extreme this is. The Sun has been running as a nuclear fusion reactor for about 4.6 billion years. It puts out an almost incomprehensible amount of energy every single second. FRB 20220610A released more total energy in its sub-millisecond burst than our Sun will produce across the next 30 years. All of that in one event from a source we can't even image directly. So what causes something like that? The leading explanation is a magnetar. A magnetar is a type of neutron star, already one of the densest objects in the universe, but with a magnetic field roughly 10 trillion times stronger than Earth's. When the magnetic field in a magnetar shifts, or when the stress on the star's crust gets too high and it cracks, the energy release is almost instantaneous and absolutely massive. That's why the burst is so short, because the event driving it happens fast and violently, not gradually. But here's the honest part. Magnetars are the best model scientists have, and FRB 20220610A still pushed that model hard. The energy output was at the extreme high end of what magnetar physics can reasonably explain, so researchers aren't fully settled on the cause. What flagged this signal immediately, though, wasn't just the energy. It was the dispersion measure, a number that tells you how much the signal's frequencies got smeared apart during the journey. The higher that number, the more matter the signal passed through, and the farther it traveled. FRB 202200610 had the highest dispersion measure ever recorded at the time, and it had been picking up traces of everything it passed through for 8 billion years. That record-breaking dispersion measure wasn't just a number that told scientists how far the signal traveled. It was actually a log of everything the signal touched along the way. And that's something most people don't realize about radio signals moving through space. They're not just crossing empty distance. They're interacting with whatever's out there, and those interactions leave marks in the signal itself. Here's how that works. Radio waves travel at the speed of light, but not all frequencies move at exactly the same speed when they're passing through matter. Higher frequencies push through a little faster, lower frequencies lag slightly behind. So by the time a signal arrives, those frequencies are spread apart. The high ones get there first, the low ones show up a little later. The more matter the signal passed through, the bigger that spread gets. Scientists measure that spread and call it the dispersion measure, and what it's really counting is electrons. Every electron the signal bumped into on its 8 billion light-year trip here. So more electrons means more matter, and more matter means the signal passed through more stuff than we expected to be there, which leads directly into a problem that's been sitting in cosmology for decades. When you add up all the normal matter we can actually see, every star, every galaxy, every gas cloud that shows up in any telescope, it only comes out to about half of what the Big Bang should have produced. The math of the early universe predicts a certain amount of ordinary matter. We find roughly half of it. The rest just doesn't show up anywhere. Scientists call this the missing baryon problem. Baryons are just regular matter, protons, neutrons, the basic building blocks of atoms. Not dark matter, not dark energy. Just normal stuff that the physics says should exist, and that telescopes consistently fail to find. The leading theory for where it went is that it's stretched out in thin, hot filaments connecting galaxies across the universe, what's called the cosmic web. The problem is that this gas is so spread out and so hot that it barely emits any light, so traditional telescopes essentially look straight through it. That's where FRB 202200610 comes in. When researchers took that record dispersion measure and subtracted out the known contributions, the matter inside the signal's host galaxy, the matter inside our own Milky Way, there was still a big excess left over. And that excess lined up almost exactly with what you'd expect if those cosmic web filaments are real and packed with diffuse ionized gas. The missing baryons were there, in the signal, the whole time. Pinning down where the signal actually came from required combining the ESCAP data with follow-up observations from optical telescopes. That process localized FRB 202200610 into a small cluster of galaxies around 8 billion light-years away. The redshift of those galaxies locked in the distance, and once the team had that confirmed, the dispersion measure gave them a direct density reading of the matter spread along that entire path. So this thing that lasted less than a millisecond essentially functioned as a probe, fired through 8 billion light-years of cosmic web, collecting a matter census the whole way. And because it worked once, it can work again. Every new FRB detected adds another line across that map, and ESCAP is finding them at a rate that would have seemed impossible just a few years ago. Deep space isn't empty. It just took a millisecond-long burst from 8 billion light-years away to show us what's actually out there. And FRB 202200610 is one signal. ESCAP is finding more, and the square-kilometer array is going to push that into thousands. Each one another measurement of matter we've never been able to directly detect before. Every new burst is another data point on a map we're only just beginning to fill in. Stay tuned, because there's a lot more coming on how astronomers are using FRBs to probe the large-scale structure of the universe. Thank you for watching.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.